with the microphone.
Oh my God.
Are you getting all this? This is out of my control.
Question to everyone on the panel. Let me just swallow first. You're kidding, right? You just made all this up, didn't you?
On the spot.
Yeah.
Well, half of it.
All right, I accept that answer.
All right. Is there a burning question? Otherwise, I'm going to start off with one. Okay, well, I will kick it off because I have multiple questions. In fact, every question that comes up just opens a whole another 100 questions for me. Yeah, and that's the best thing about it. Exactly. So, and I'll just qualify this. I'm an ecologist. I work with real things I can see and touch. And when I measure them, they're still doing that thing.
There's only one of them.
No, there's millions of my ants. But
They're not in two different places.
yeah, apparently they are. But so my question to you guys, and I want you both to answer this from your perspectives, is when you can't use your senses, your touch, your sight, your hearing, your smell, with all these things, and you rely on mathematics and concepts and ideas, how then can we confirm that these are real ideas and real concepts that we should, and for want of a better word in science, believe?
Well, even things that can't be visualised, the formulas still make predictions that you can test in a laboratory. So the wave function that was talked about earlier on, it's quite easy to visualise a probability distribution function. You have some curve and it says it's got higher probability of being here or lower probability of being there. That's something that we can visualise quite easily. The wave function is actually more than that. It's not probabilities, it's complex numbers. So they can be positive, they can be negative, they can be multiples of the square root of -1. So every point in this distribution is this more complex mathematical object that you can't really visualise. So we can no longer visualise it in the same way that we can a probability. Nonetheless, using the mathematics behind it, we can make predictions for what should happen in the laboratory. And it's those predictions that we can confirm whether they're correct or not.
Okay, can I do part 2 of that answer?
Yeah.
Okay. No matter how weird and theoretical the physics gets, it's not considered real confirmed physics until somebody does an experiment. So what qualifies as an experiment? And actually, in my opinion, an experiment is when you take the abstract, the theoretical or whatever, and you eventually tie it back to something where a human being actually has to use his or her senses to note something. So the whole of CERN, I will argue later. Yeah. The whole of CERN, you've got all this, you've got CERN, you've got all that happening, but it isn't an experiment until a blip appears on a screen or in a list of numbers that a human being will eventually have to sit down and look at it and say, right, I judge that as having been observed.
Can I disagree with that? So using the same argument, you could argue that pure mathematics is not a science because it deals with things that can't
I'm talking empirical science. I'm talking empirical science.
Okay, well,
if
you're talking empirical, then of course by definition it's practical.
Yeah. No. I'm not.
That's what empirical means.
Yeah, I'm not including maths in that. What distinguishes maths from science? Well, actually, but in applied maths, not necessarily. But what distinguishes maths from the empirical sciences is that in the end, no matter how abstract it gets, until there's a line that eventually leads to somebody having to use sense organs, then it's not considered an experiment.
We have an audience member that would like to say something.
I want to contest that. Contest that because you talked about until you assign a number or see a blip on the screen.
Yeah.
Now, when you see a blip on the screen, it's just a blip on the screen.
No, I know it is. Yeah,
but
of course.
in order to think of the position of a voltmeter against a dial as measuring current, you have a huge theoretical construction.
Oh, no, of course.
No, we're done.
Yeah.
So all of these observations that you talk about depend upon a theory.
Of course they do.
Which cannot be tested empirically. There's no way of testing the law of conservation of energy because every measurement that you make on the device assumes the law of conservation.
I'm not disagreeing
Wait a minute.
with you. I'm not disagreeing.
The point is that you're saying that the theory means nothing.
No, didn't say that.
You're saying it's not experiment.
He didn't
it's not.
say that.
I didn't say that.
You talked about empirical science that you distinguish empirical from theoretical, from pure mathematics or whatever.
Yeah.
Because you need to be able to make an observation by a human being. And I'm saying the observation is just a blip, has no meaning, says nothing.
No, I agree. I'm not disagreeing. I completely agree with you. Maybe you misunderstood my point.
I thought your point was that to be empirical, you have to have evidence or measurements confirming it within an approved or agreed accuracy. What I'm saying is that the measurement itself cannot be tested for accuracy. Because the devices that you, for example, law of conservation of energy, because every device, every measurement you make assumes the law of conservation of energy. So it's a circular argument.
No, it's not. No, okay.
I'm going to give you one more chance, Steve, to reply to that, then we're moving on.
I'm not saying that this is I'm not saying this is absolutely logically tight. No, yes, there's gaping holes in the whole process. All I'm saying is that look at string theory. There are a lot of people working on string theory, but most physicists are kind of thinking, well, until you actually make something that I consider a prediction that we'll be able to do a measurement on, then really it's interesting stuff, but it isn't physics until it gets to that point. We can't. It's still. I'm not going to call it real. I'm not going to call it real until you make a prediction that I can test. Now, I'm not saying that whole chain of logical connections between them is unbroken and unflawed and unquestionable. No, that's not what I'm saying. But I'm just simply saying that what counts as an experiment at some point has to tie that whole string of things that are happening, that whole string of events, to a sense organ. And
So
if that
Steve
doesn't
is-
happen, then it's not considered an experiment.
Stop for a second.
Why is law of conservation of energy accepted when it doesn't satisfy when it doesn't satisfy any of the criteria used to measure?
No, I don't disagree with you. I'm not saying that.
Guys, this is a discussion you have
let's
to
have this
have at the
discussion
bar.
later. I
I'm
agree
sorry,
with you.
you
I agree
really
with you,
do.
but I think you're missing my point.
Yeah, you can absolutely have it later. But this is one of the good things about science, right? It's about arguments. We have another question from the audience. No, Steve, you keep that one. There's an audience microphone.
Oh, there is. Oh, okay.
James.
Yeah, my question is for Steve.
Yep.
So next time I'm in a pub argument, I'm going to assert confidently that the multiverse theory is different from the other thing.
Yeah. They're conceptually totally
Yes.
different.
Many worlds.
One's cosmology and one is quantum mechanics. Yeah.
That's what I want to know. Give me more ammunition for this argument. How is the possibility of multiple universes different from there being multiple possibilities
Well,
of things?
in our universe, perhaps we're getting this many worlds quantum mechanics happening, and maybe not. I don't think it is. But we've got the universe that we can see and that we can observe or whatever, and we've got a set of theories or whatever. However, you see, the original concept of the Big Bang is that it started off as a singularity, right? But one thing that quantum mechanics tells us is that things that we thought are continuous are grainy, and one of the possibilities, but it's still only vague, it's not fully worked out, is that in fact space and time is grainy. And so if that's true, then you can't have an absolute singularity because the whole universe can't be any smaller than whatever the minimum grain size of the universe is. And there's this thing called the Planck Length. So it's a speculative, but there's this idea that the smallest unit of space is this thing called Planck Length, which is, anyone remember what a 10 to the minus 34 of a metre or something like that? I can't remember. Yes, I think it's 10 to the minus 34 of a metre. Now, if that's true, then you won't have a singularity. In the same way, if there's any chemists still here, we talk about absolute zero. What happens is absolute zero, they came up with absolute zero when they looked at the contraction of gases with temperature, and they extrapolated this nice straight line, and they said when T is equal to 0 Kelvin, what we now call 0 Kelvin, then the volume of that gas is zero. Now, the volume of the gas can't be zero because it's made up of molecules. So in the same way, it could be that something similar happens when you go back to the Big Bang and compress and compress and compress, and you get to the point where it can't be zero volume because maybe space is quantum as well, and so there's this... Right. Now, if that's the case, then it could very well be that this little bubble that popped out, which is our universe, is just another bubble that's nucleating on something that sometimes the string theorists call the brain, as in short for membrane. Yeah, as in short for membrane. Like you look at the bottom of your beer glass and you'll see that a bubble will nucleate on the little laser etched scratch on the bottom of the glass, and then it blows up. And one way of thinking of the Big Bang is like that. Our little bit, what we call the universe, nucleated at some point off some point in space that's the Planck Length wide. We don't really know why it nucleated, that's a whole other question. But there's no reason why another universe, which is completely out of communication with ours, because these bubbles can't talk to each other, another one nucleated at a different time, and that universes are popping in and out of
Is
existence.
that a multiverse, though,
That's
or
the
many
multiverse.
worlds?
That's the multiverse.
Okay.
Right? The many worlds thing is something that's happening right now. This space I'm in right now is just full of all the other unrealised possibilities, or what to my eyes are unrealised quantum possibilities.
Like you sitting over there having dinner.
Yeah, in there, or I could be, yeah.
The difference is this occurs in the same universe.
Yeah.
The other one proposes there are
Separate
parallel
universes. Yeah.
Same bubble, different bubble.
So you're
But
saying multiverse is more plausible
Yeah.
than many worlds?
To my ear, yeah.
So I disagree with any assertion that any of these theories are superior to the other.
No,
And hang on.
Sorry, go
The
on.
reason is that none of them can be tested because they all make identical predictions. Every interpretation of quantum physics that we have today is completely consistent in the predictions that it makes. If you have a theory which is completely consistent in what it predicts with another theory, by definition, you cannot experimentally test which is which. Therefore, going back to what he was saying earlier on, it's not real science to even talk about it because you can't experimentally determine it.
And moreover, if we're going to go for the simplest explanation, then the parallel universes one is uncountably, infinitely more complex than one where there's just one reality happening at any given time, and it's a series of coin tosses.
So actually, James, it probably comes down to what you believe.
It's a question of taste.
Yeah.
That's it.
Like,
It's a
do you
question
like
of
beer
taste.
or Guinness? Bubbles, one bubble, two bubbles.
Hindu or Christian?
Yeah. Yeah.
I'm happy with that.
Could you
Someone
do
else
that?
can ask a question.
Could we trial that argument maybe in another pub another time?
Oh, yes.
Okay.
Oh yeah,
Let's
but I'm
go
not
no
saying.
further.
I'm saying the only reason that I find the concept of the multiverse palatable, and I don't find is not because I think it's more believable. It's just simply as I was saying, it isn't just a coin toss. It is a continuous series, and in many cases, of an uncountable infinity of possible outcomes. It just seems so much extra rubbish to explain. Now, it could be right. I've got nothing to say, but it's just...
But there's no experimental
It's
evidence, and as Pete
extraordinary.
said,
Something is complex, therefore it's unlikely to be true. It's a pretty weak...
No, I'm not saying unlikely. No, just unpalatable. That's all. It's just a question of taste.
unpalatable to you.
Yeah. No, we have no basis to judge scientific validity.
Yeah, I agree.
It just seems unpalatable to me, that's all. That's as far as I'm prepared to go.
Okay.
Whereas
Okay,
the multiverse it's one universe at a time. There's perhaps a countable infinity of universes.
That's more
I can
comprehensible
deal with
to
that.
humans.
What do I,
All
just
right.
what do I mean by countable infinity? What? Sorry, what?
Michael, can you grab the microphone? There's a question over there.
No, sure.
complex numbers, they're all uncountable.
Yeah.
I love it.
do without it.
I don't want to stop that.
Oh, yeah, okay, so let's just stop there.
Okay, we have
question of
another
taste.
question from the audience.
Just about the last point. Einstein said, when he developed his theory of general relativity,
Yeah.
that the beauty of the equations convinced him that was correct.
Yeah, of course.
He didn't wait for,
Of
he
course.
did not wait for any
Oh, I know.
information.
Because he's a theoretician.
Is that in the same way that patterns in music have a beautiful pattern, if you like, and noise in music has a non-pattern.
Come on, these days noise is considered music.
To you, Pete? The simplicity of the pattern and the beauty of that. Yeah.
No, I agree. You don't pick theories. You go with theory. But what do we mean by beauty? Beauty, we mean that it is that you can explain everything that you're trying to explain with a kind of simplicity that suggests that you haven't fudged it. Because it's easy to get things to fit by fudging. You know, you look at Ptolemy's explanation of the motions of the planets, that the Earth is at the centre of everything and everything's on wheels within wheels. And it worked, it fitted nicely, but only because Ptolemy had added so many damned wheels and adjusted the speeds of all the wheels, you can make it fit anything. It's called an overdetermined...
But you couldn't distinguish that experimentally.
Yeah.
The theory we now take, so distinction with what we can now consider science.
Until Galileo pulled out his telescope and saw that there were phases of Venus. Then all of a sudden Ptolemy's model was rubbish.
You could add a few more fudges to Ptolemy and receive as well.
Oh, sure.
Since I have the microphone,
Yeah.
a question about entanglement. which
Yeah.
actually was not discussed here.
It was, but the
not
word
article.
wasn't used, yeah.
Well, two particles, let's say, split. They're entangled.
Yeah.
But if there is a big bang, there was a singularity,
Yeah.
wouldn't it mean that all particles in the universe are entangled in some way?
I don't think I'm qualified to say.
I don't think we know enough about the laws of physics at the early part of the universe to know the answer to that. But certainly there must have been entanglement because it's a feature of what's called quantum information theory that I work in, that entanglement is something that's conserved. Like mass and momentum, there's a certain preservation of entanglement. So if we observe entanglement in the real world today, there must have been at the beginning of the universe. Whether that means that there was everything being entangled, we don't really know, because we don't really know what the structure of the singularity was. But it seems certain that there was entanglement earlier on.
And are there any experimental approaches to solve the problem?
Well, I think it's highly unlikely we'll be able to do an experiment that traces all the way back to the singularity. Look, I'm not a cosmologist, but that's the sort of question a cosmologist would answer, not a quantum physicist. Yeah, exactly.
Well, the thing is, it seems now you can't answer an experiment.
Steve, can you grab a microphone if you're going to talk?
Sorry, yeah. At the moment, it seems like you can't answer it experimentally. But don't forget that when Einstein predicted gravity waves, he said no one will ever be able to detect these. They're just too subtle. And 101 years later, they were detected.
But that was a question of subtlety.
Yeah.
It's the question of principle, as opposed to...
Oh, and sometimes...
It's like in principle you can't do it because... you can't do this because our observations in astronomy...
Yeah.
We deduce how far things are from colour and various other things.
Course.
And all our observations depend upon theory, and therefore they can't falsify the theory they depend on.
Of course.
Only logical inconsistency could lead to some inelegance, which is why we're of Ptolemy, rather than fudge a bit more.
Well, okay, let me give an example. You see, you look at it now and you say, well, in principle, there's no way we could do those experiments that would tell us what happened right at the beginning of the Big Bang. But you see, in 1888, an astronomer said, we're now reaching the limits of what we'll be able to tell about the stars because at that stage, nobody knew about infrared, nobody knew about radio waves, nobody knew about gravity waves, nobody knew about... And within minutes of him making the statement, spectroscopy was there was a bunch of, infrared was discovered and a bunch of other things happened. So it is conceivable that some phenomenon that we didn't realise was implied in the theory pops out, and then it allows us to do that.
In exactly the same way, it's quite possible that in 10 years' time, the laws of gravity that we have will cease to function. That
of course.
I mean, in this sort of absolute philosophical possibility, you're right. But I'm talking about the internal structure of scientific theory and scientific practice. You cannot do science purely on the basis of observation, otherwise we would still think the world is flat.
No, of course not. Of course not.
And I'm going to halt it there because, I don't know what you're going to... Actually, I'll pass it to Laszlo. But that's exactly what you can continue arguing about forever, right? Forever. Because that scientific theory is what humans do. Laszlo.
if I got this. Peter, could you just speculate on how quantum computing is likely to turn up in our day-to-day lives?
Yeah, the first thing is the NSA will read all your emails. That's the very first application, I can guarantee you, because that's the application that gets all the money. The really exciting applications have nothing to do with code breaking. I don't care about that, you don't care about that, only the CIA and the NSA care about that. The really exciting application, in my opinion, is called quantum simulation. This is where you have quantum systems like the atoms or the molecules, and you're trying to simulate their interaction at the quantum mechanical level. Why is that interesting? Well, if you consider drug design, for example, you want to simulate the interaction of a drug molecule with some organic molecule, or genetic medicine, simulating the interaction between genes. That's, again, at the molecular level. This is a quantum mechanical process. So, from a medical point of view, this will enable rapid development of new drugs. Previously, we would have to make thousands and thousands of laboratory tests. Now we have the computational power to do it on a computer. Another really important application for quantum computing is optimization theory. So optimization is something that, whether you know it or not, it appears all the time. Every time you get onto the train operator has done a lot of work to try and make the timetables as efficient as possible. That's a really, really hard problem to do, because you've got all of these constraints. You want the people at this station to be waiting the smallest amount of time. The people at that station have to walk from there to get to that platform. All of these simultaneous constraints need to be optimized. It turns out that these kinds of problems are really hard on classical computers. Quantum computers can speed many of these problems up quite dramatically. So this will affect things like efficiency of train systems, allocation of resources in the economy, traffic networking, even the order in which the traffic lights change. Things like that can make huge differences to our everyday lives.
So let's say climate change modelling.
That's hard to know. I don't know enough about the mathematics behind climate change modelling. To my knowledge, based on the maths I've seen, which is largely solving systems of differential equations, it isn't clear whether that will have any immediate applicability to quantum computing. But certainly, if it can be expressed as some kind of optimization problem, then probably yes. Okay. Perhaps the most exciting thing about quantum computing is that it's a very new field, and we simply don't know most of the applications yet. Every year, countless new ones get described. I've described the ones that, to me, are the most exciting so far, but in 10 years' time, we'll probably have a much better understanding of the field.
Okay, great, thanks.
Peter, can they optimise these systems purely because they can simultaneously see the options available to them through the superposition?
The way to think about it is, remember the algorithm I described, Grover's algorithm for searching the unordered database, the phone book that isn't ordered by what you're looking for. So you can call the phone book what's called an oracle. Imagine it's this black box and you can ask it a question and it spits out an answer. If the question you're asking isn't what am I finding in the phone book, but rather, is this a solution to the problem? You use Grover's algorithm through this oracle, and it'll give you the answer to the optimization problem. So Grover's algorithm is directly used for optimization problems.
Is that understanding that there is not one correct answer, but many?
Oh, there can be multiple solutions to optimization problems, and some quantum algorithms find a solution, some quantum algorithms find all the solutions. Obviously, the latter is going to be more difficult in general than the former, but it depends entirely on the structure of the optimization problem, because there are many, many different types of optimizations you can do.
Has anyone got an optimisation problem immediately that they'd like to
Don't say online
Peter
dating. But in all fairness, you probably could get some really good Tinder matches.
I heard a story a couple of days ago how a couple of geeks got together in the early days of, or relatively early days of computing. I think it was back in the 60s or very early 70s. So some undergrads got together and they charged people money. They said, look, here's a questionnaire, fill out the questionnaire, send us the questionnaire, and we'll get the computer to match you up. And then what they did was they crossed out all of the questions except for the one that was your address or your postcode, and they just matched you up with people that were walking distance from where you lived, and apparently people swore by it.
That's exactly what Tinder does. It says this person is within a 5-kilometre radius. That's it.
Are you serious?
Well, and then you swipe left or swipe. You're doing the optimization yourself. You're saying it puts things in a radius, and then you do the optimization by swiping left or swiping right.
So you can change the algorithm.
Absolutely.
Oh, I'm going to try that.
They have a visual interface. So
Yeah, well, that's true.
Questions from the audience? Any more? Yeah, James. Microphone.
I can bring us back down to earth with this question. Pete and Steve, can you name, do you remember the shitty movie about Einstein applying his knowledge of stochasticity to dating?
John Nash.
No, there was a movie. I know the movie you're talking about. I studiously avoid watching it. I think I walked past the television when it was on rerun.
Tim
once.
Robbins was the love interest.
Yeah. And it was called. It was
Yes.
called. And I just walked in the scene where they had the guy dressed up as Einstein talking. I'm thinking.
How many times have you
I'm
seen
not
that,
watching
James?
this film. Oh, no, wait, don't tell me it was called. It was called.
Once was enough.
Not.
What's the name of it?
Does anybody know what I'm talking about?
It was one word. It was an. It was. It was a.
It's not even a word.
Oh, it wasn't a word. Oh, okay. It was.
Is it an acronym?
Oh, what was the? I've forgotten. What was it?
It's called IQ, everybody.
Oh, that's right. Yes. No, I studiously avoided it. I knew
I
it was
might
going to
watch
be
that.
But there was
Ryan
another
falls in
movie.
love with
But
Tim
another movie.
Robbins.
There was another movie which I actually made a subtle reference to in my talk, which nobody noticed. Which I would rather sit through IQ than that movie again. A movie called What the Bleep Do We Know? Yeah. I made a reference to it in one of my slides. I said, "What the bleep is a wave function." The only reason I watched it was my brother-in-law was running a cinema up in Byron Bay, and he said, "Steve, the people at Byron Bay love this film. I want to know your opinion as a physicist."
And
Basically, just so the people who don't know what the movie's about, basically what it does, it starts off by talking about some of the weirdo quantum mechanics stuff that we talked about, and it was a little bit over-egged, but in the first 20 minutes it didn't say anything that wasn't totally, would have been totally objected to by physicists. It was just a little bit, but then they said, all right, all this quantum weirdness, and so therefore now human minds can spiritually influence the outcomes of snowflake evaporation, and they started going on about homeopathy and all sorts. Yeah, and all frozen, all that stuff. So for the first 20
Ian's
minutes,
seen
I'm
it
just sort of
multiple
going,
times too, it appears.
And I had to watch it because my brother-in-law, I was being a movie critic
Yeah.
rather than, Yeah.
It's a commercial job.
And I would much rather watch IQ over and over again than have to watch that one again.
All right, I'm going to wrap up Q&A with these guys and ask you one more question about the future of quantum research. And Pete, Steve, what do you see as one of the really big gaps and an important gap to fill in quantum research?
You go first because you're actually doing it, and I'll see if I can fudge something.
So I'll speak on behalf of my area of research, which is quantum computing, because there are many different facets of quantum physics in general. The real exciting thing, I think, is finding more applications for quantum computers. I alluded to this earlier on. We do have quite limited understanding of what we can do with them. Already, some of those things are quite exciting, and I expressed to you some of the reasons why I think they're exciting. But if you think about classical computing, we've got algorithms for doing just about everything under the sun. There's barely anything that you can't describe using a piece of code that you can write on your classical computer. Now, it may be fast, it may be slow, that's a separate question, but pretty much everything can be expressed as a piece of computer code. The question is, what are the limitations on what we can write as code on a quantum computer? How far can we go? What problems can we solve? But most importantly, what problems can we solve such that there's a huge speed advantage compared to classical algorithms? Because quantum computers don't speed up every type of algorithm. They apply to a limited class of problems, and fully understanding that class is still an open question.
Okay, I thought of something, and I think Imi's going to agree with me because he pulled a face when I was talking about this, and I think he was pulling the face for the same reason that I would have pulled the face. We talked about quantum electrodynamics, and I said that it works to 12 or 13 decimal places, so there's something right about it. But I did hint there was a gaping hole in it, and it's this thing called, and tell me if this is what you were worried about, and this renormalization. Was that the thing that? Yeah. Okay. Now, without getting too technical. The way the quantum electrodynamics works is, do you remember in the discussion about quantum computing that it was discussed that you have the wave functions interfere with each other. Now, in quantum electrodynamics, the way it works is you work out every possible path that, say, an electron can take through the system, and you work out the wave function for each of those possible paths, and then you add them all. And in fact, some of the paths go backwards in time. That's the thing. The funny thing about quantum electrodynamics is you have to take into account the paths that are going backwards in time, and then you add them all up, and then they all interfere with each other, and all that's left is what actually happens. Now, in adding up all these different terms, you get this problem in that there's an infinite number of terms, and it is possible to add up an infinite number of terms so they converge, okay? If you have 1 over a quarter, yeah. So, but okay, if you had an infinite number of terms, but they're each getting smaller, it is possible to add up to a finite number. However, in quantum electrodynamics, that doesn't always happen. That when you add up all these infinite number of possible paths, you end up with something that blows up to an infinite amount of energy, and you go, oh bugger. So then what they do is this process called renormalization, which is, to caricature it a bit, is you've got the two sides of the equation, you're adding up all your terms, and then you've got another bunch of terms here, and then you subtract infinity from both sides of the equation until you're left with the bit that's finite. That is a kind of a caricature of what renormalization is.
But renormalization has still not, is still a problem.
It's a problem. But it's a...
mathematical prizes if you solve.
Yeah.
It's a bit like Fermat's last theorem, maybe.
No.
I loved
It doesn't fit in the side of the column.
Yeah. So basically what they do is you're adding up all this infinite number of possible terms. Now what happens is normally when you're solving a problem by adding up an infinite number of terms, you don't have to add all infinite. You can make some decision, once the term gets smaller than a certain amount, I'll just stop adding them up. And renormalization is you say, I'm going to add up all the terms down to a radius of 10 to the minus 15, anything below 10 to the minus 30 metres, and I won't add up the terms. Yeah, we'll just ignore it. And you get the right answers. And if you were to go a little bit further, you'd still get the right answer. So that little those last few terms or whatever, or those infinite number of terms but confined to this tiny little space, you can ignore them. However, there's no logical justification for ignoring them. It's just if you do ignore them, you get works. And I think that's a gaping hole in the logic of quantum electrodynamics. There's something right about quantum electrodynamics. It works to 13 decimal places, but there's a logical hole in it. And I think that's, in terms of theoretical research, I think that's an important...
Is this something that mathematicians are sitting in a room by themselves for 10 years trying to solve type of thing?
Mathematicians, theoretical physicists, mathematical physicists are working together on this simultaneously. John Bayes' thing. So historically, now 30 years...
Hang on, Emmy, do you want a microphone?
Okay.
Microphone. Sorry, thanks, James.
About 30 or 40 years ago, Dieudonné wrote a book on mathematics, on the current state of mathematics, and in each section he put applications of physical sciences. When it came to category theory and stuff like that, he said none known at this moment. And 3 years later, 3 Fields medals were given to theoretical physicists for applying category theory. So the current view is that the right way to look at particles may be in terms of higher or n categories. But I'd like to say one thing about I think the fundamental problem quantum mechanics or quantum theory, which has been addressed, is quantum theory and relativity, general relativity, are still not compatible. There's a lot of work on that.
It sounds like there's huge gaps in physics, and we should...
Bayer was working on this in Zurich.
Sticky taped
Yeah.
quantum theory
And relativity.
Yeah. That's an very important point. Now, the two... the two most successful theories of the 20th century, quantum mechanics and relativity theory. At this stage, There's no logical connection between the two. However, what quantum electrodynamics did, they said, right, let's assume relativity is true, let's assume quantum mechanics is true, and we'll run them,
let them
side by
coexist.
side, and we get the right answer. But we still don't know why quantum mechanics and relativity coexist simultaneously. They're like they're unrelated. There's just no connection, no obvious logical connection between the two.
This is why
Yeah.
logical deformation can never be used in physics.
Okay.
And I'm going to call it a night on that because I think those 3 gaps. No, don't. No. Are you serious?
You're talking about an infinite number of things. I've just heard somewhere that if you get to 10 to the 92, that the infinite number of things starts to repeat themselves. Is that true or not?
Depends on what you're talking about.
I don't think anybody cares.
Yeah. I don't know the context of where you were told that story. It might be true in some particular example. I don't know.
No, think of pi.
Pi never
Goes on
repeats.
forever, but it never lives.
Or think of trying to find an algorithm for finding prime numbers.
You guys could continue that conversation tomorrow. I know. So actually, I'm going to ask you guys to thank Dr. Peter Rodhe and Dr. Stephen Bosi for coming and explaining quantum theory. And thank you guys for staying till the end and committing to understanding some of this. I don't know whether you have or not, but I certainly have learnt a huge amount about quantum watt tonight, and I'm incredibly grateful. And I feel like I can very genuinely encourage people to go into physics from now.
And a round of applause for Kirsty for organising all of this.
Now, I will say that the next Science in the Club is July. I think it's the 19th, and we have Toxic Australia, venomous and toxic animals. We have the Nutty Professor coming down from James Cook University to talk about Australian animals. So please join us then. And thank you very much. Have a good evening, everybody.